V, okay? So I write, for example, the inner product of V with, say, W. This is going to be V with the sum of AI and UI. This is what it is going to be, okay? You know, if I wish I can put it here or here, it doesn't make any difference. Then I can write this as, by the way, these UIs are the elements from U actually, because you are talking about the span of U. So I can write this as a sum. So I can pull this sum out, and I can also pull these numbers out. So this is going to be AI, for example, bar times the V and what do you call UI. Okay. So now I can write this as, I pulled this sum out and I pulled this AI out, so it's going to be AI bar, so inner product of V with the UIs. But the UIs are the elements of U, and I know that V is orthogonal to every single element in U. So V is going to be orthogonal to the UIs as well. So this means that this inner product is also 0 for each I. So if this is true, that means that this is equal to 0, because this guy is 0, for any I. So the inner product is 0. So what does this show? We picked an element from a span of U, and we showed we picked an element from U perp, and we picked an arbitrary element from a span of U, and we showed that V is also orthogonal to every element in, so I can say that for all W in span of U. So this means that V also belongs to the perp of the span of U actually. So V is here and V is also in the span of U perp. So what does this show? That span of U perp is equal to the U perp actually. Okay? Now let's come to the fifth part, and let's say that this intersection is non-empty. Then I would like to show that U intersection U perp must be 0. Okay. Why this should be 0? Now as we are assuming that U intersection U perp is non-empty, so there must be, say, a vector U in both. U in both. Okay, U must belongs to U and U must belongs to perp of it. So this means that U is in U and U is in U perp. But what is the meaning of U being in U perp actually? This means that U is orthogonal to every single element in U for all V in U. Okay? Since U is in U perp, so it is orthogonal to every single element in U. And I know that U is also in U. So if I take if I take this V in particular U, then the inner product of U with U is also 0. And if the inner product of U with U is 0, that means that the norm of U is 0. And if the norm of U is 0, the vector U must be 0 itself. So we picked an arbitrary element from U intersection U perp, and we showed that its intersection is, you can't have any intersection. If there is something in the intersection, that thing should be vector 0. So this is the property 4 of it. Now the fifth says that imagine 0 is in the intersection of both. Then in the intersection of the perp, you're going to have, what do you call, U perp actually. Okay? Or maybe this is something that you should prove for yourself. This, fifth and fourth, I'm saying that these are your little exercises actually. Let's say think about the path H. U contained in span of U is trivial. Okay, so this is trivial by definition. We know it from our first course in linear algebra. So the only thing that I need to show is that the span of U is a subset of U perp of the perp. Okay. By the way, let's write what would be the U perp of the perp. So the U perp of the U perp is going to be the collection of those U's from U perp such that which are orthogonal to all elements in U perp. Okay? So U perp is a collection of those vectors U which are orthogonal to every single element in U perp. So therefore, U would belong to the perp of the perp actually. Okay, it's going to be in the perp of the perp. So this is U perp of the perp. So let's take, for example, a vector V from the span of U. V from the span of U. Span of U. So this means that V must be a linear combination of the elements from U actually. Okay, so V would be the sum AI UI. Now I need to show that this V is orthogonal to every single element in U perp actually. Okay. Where the UI's are from U. Okay. This is what it is. And I need to show, we want to show that V is orthogonal to W, okay, is equal to W for all W in U perp. Okay? U perp. So let's compute it. Now, so this is what we would like to show. Let's compute the inner product of V with W. So if you compute the inner product of V with W, okay, this would be the sum of AI, UI, and W. I can write this sum as sum of AI and UI inner product with W. Now tell me, what is the inner product of UI with W? I know that W is in U perp, so W's inner product with every single element in U must be 0. So these UI's from the U, so their inner product with UI's must be 0, and hence this must be equal to 0. So this shows that V is orthogonal to W for all W in U perp. So if this is the case, V would belong to the perp of this set actually. Perp of this set, which is the perp of the perp. Okay? So this is what is really the proof of this part actually. Okay? So what are the benefits that you can get out of the orthogonal complements? Why orthogonal complement is really a complement, okay? Because of the fact that I'm going to prove now actually. So what you can do always, so imagine you want to, find say a direct sum of a given inner product space actually, okay? Then you need to do what? Take a subspace of that inner product space, compute its direct sum, then the direct sum of the inner product is subspace and its perp is going to be, orthogonal complement is going to be equal to V. So in other words, V can be always broken down are written in the terms of subspaces and their orthogonal complements. Okay, subspaces and their orthogonal complements. So here is a proposition, a theorem, whatever you call it. Let's call it a theorem. So it says that if U is a finite dimensional so it's a finite dimensional subspace of inner product space V, which may be finite dimension and may be infinite dimensional. Like, there's no restriction. then V can be always written as a direct sum of U and U per part. Okay, U per. So you can always write it. I mean, if you remember what do you mean by a direct sum? So I would say that V is a direct sum of say two subspaces A and B, if and only if every element of V can be written as the sum of these two elements, okay, and the intersection of these two subspaces is 0, is trivial. Or you can also say that every single element of V can be uniquely written as the sum of elements from A, element from B actually. So this is what the definition of the direct sum is. In case when V is infinite dimensional, if U is finite dimensional, obviously U perp is going to be infinite dimensional, so that their sum should be infinite. But in case of the finite dimension, we also have what you call the Eigenvalue theorem actually, so you can also talk about their dimensions. Anyway, so if U is a finite dimensional subspace of V, then V can be written as the U, the direct sum of U and its U perp. In particular, for each V in U of V in the inner product space V, okay, we can find there exists a unique vector, a unique U such that V can be written as a U plus V minus U, such that V minus U belongs to U bar. That is that every V can be uniquely written as an element of U and U perp actually, because V can be written as U plus V minus U. So if this is in U perp, so if U is unique, V minus U is unique, hence V can be written as the sum of an element from U and U perp actually. So that's what, so this is what really is another way of saying it actually, that okay, if V is the direct sum of U and U perp, then each V in V, for each V in V you can always find a U such that V minus U must be U perp. And hence you can write it uniquely. So here's a quick proof of it. So U is a finite dimensional subspace, so you can always find an orthonormal basis of it. So let U1, U2 up to UR be the orthonormal basis of U. Okay, so it's an orthonormal basis of U. Okay. Now, if this is the case, if you take say V in V, by the way, first of all, in order to show that V is the direct sum of U and U prime, okay, So one thing that we already have proved actually, that since the 0 is in U, because U is a subspace, so 0 must be there. So the U intersection U perp is equal to 0. Okay, this is what we already know actually from our previous result. The only thing that we need to show now is that every element in V can be written as a sum of element from U and an element from U perp. This is what that I would like to show. Now for V in V, for any V in V, do the following. And do what? Consider this one. V can be written as, say, the sum that goes from I equal to 1 to R, okay, in a product of V with UI, UI, okay, V with UI, UI, because what? Because I know that this is an orthonormal basis. So if I have an orthonormal basis of this is not UR, subspace U, okay, and then this will be an element in U actually. For sure this will be an element in U, okay. Plus V, so take V, take this element in U and subtract, what do you call, the element, what do you call, I equal to 1 to N, okay, I equal to 1 to R, V, UI, UI. Okay, so what I did, I took V and added this vector and subtracted this vector. Now this vector is like a vector U. Okay, so this vector is like a, what do you call, vector U, and this vector is like a vector, what do you call, V. Okay. By the way, why this is an element in U? Because this is one of the element in a span of U actually. Okay, span of U. Because you can pick an element from U and you compute its linear combination, that linear combination would also be in U actually, so that's an element of U. While this element is really what do you call V minus U. What do you call V minus U? So what we did, I picked an element from V, okay, and I wrote it as an element from what do you call U, and this, I'm claiming that this element is an element in U perp actually. It's an element in U perp. So if it is an element in U perp, then what will happen? Then V has been written as an element of U and U perp. Okay. So this will prove that V can be written as a direct sum of U and U perp. Okay. The only thing finally then that will be proved is that the U is unique actually. The uniqueness of it. Okay, so let's now show that V minus U is an element in U perp. Okay? This is an element in U because this is a linear combination of element in basis of U actually. So it's an element of a span. Span is always equal to the subspace itself if the U is subspace. So we know these facts actually. So you always have to keep the basic results in your head when you are moving ahead actually. Okay? So the claim is that V minus U belong to what do you call U perp. By U I mean, okay, this vector. So this is U plus V minus U actually. Okay, so V belongs to U perp actually. So in order to show that V minus U belongs to U perp, I need to show that V minus U is orthogonal to every single vector in what do you call U actually. So it's orthogonal for all W in U. Or in particular, it is enough to show that V minus U is orthogonal to the basis of U actually for all I equal to 1, 2, 3 up to R actually. So if V minus U are orthogonal to the basis of U, they will be orthogonal to the all linear combinations as well. So it will be orthogonal to arbitrary element U actually. So what should I do? So let's compute, say, V minus U and its inner product with UI. So the V minus U is really V minus sum that goes from I equal to 1 to R, VUI inner product with UI, okay, and its inner product with UI. This is what that you're going to get. Okay. Then I can simplify this as VUI minus the inner product of the sum that goes from I equal to 1 to R, VUI and UI and its inner product with UI. This is what that you're going to get. By the way, if I am using index I for this, let's talk about, say, uj here. Okay, so let's call this vector as uj rather than I actually, because this would be confusing if I use the I for both indices actually. So this would be vuj. So it's going to be vuj minus, I can pull this sum out, I that goes from 1 to R. I can pull these numbers out as well, VUI, and what is going to remain inside is the inner product UI uj. Okay? But this inner product UI uj is really equal to delta ij. Delta ij. So in this sum, which term would survive? The only term that would survive is going to be the term when I is equal to j actually. The rest is going to go out. So you have, the rest are going to be 0. So VUJ minus, so the only term that is going to survive is going to be VUJ, and here is going to be uj, but the inner product of uj with uj is 1. So this is going to be vuj. Then vuj minus vuj is really equal to 0. So what does this shows? This shows that v minus u is orthogonal to the basis of u. If it is orthogonal to basis of u, it is not difficult to show that it is orthogonal to every single vector in u actually, and hence we can show that v minus u is orthogonal to u part. It is orthogonal to the entire element and hence element in u part. The next would be to show that so this shows that every element in V can be written as U plus V minus U, where U is an element in U and V minus U is an element in U part. Hence, V is equal to U plus U part. Okay? But from the last theorem, as we know, since U is subspace, so since U is subspace, 0 belongs to it, and if the 0 belongs to the U, then you know the intersection of U and U perp is also 0 actually. So since these two conditions are satisfied, so we're going to say that U is the direct sum of U and U perp actually. Okay, and if U is the direct sum of u and u perp, every single element in V can be written as the sum of u and u perp. So it's not difficult. It can be uniquely written as u and u perp. Okay. So this really this really completes the proof of it. So what does this result is telling you? That if you take a subspace of inner product space V, then inner product space can always be written as the direct sum of that subspace and what do you call the perp of it. Okay. Here is the theorem. Next theorem. Okay. So it's good to that if we collect all these properties. Okay. So if U is